So, the question is there a principled way to get estimators from data? And the way one could do this is by looking at what is called as the likelihood function. Likelihood function. And the likelihood function looks as follows, right. So, let us take the example. It is easy to explain the smaller example. Let us say 1011 was our data. Now, now we are going to say the x-axis goes from 0 to 1, and it is all choices of p that could have possibly generated the data that we see, which is 1011. Now, for every value of p, we ask the question, well, I have seen this data. If the true p was this, what is the chance that I would have seen this data, right? So, and now we can plot that chance, right? So, this is the probability that your first random variable, which is the first outcome, was 1, the second outcome is 0, the third outcome is 1, and the fourth outcome is 1. Now, you can plot this, right. So, for every value of p, you can ask what is the probability that I observe this data, and that is what we are calling as likelihood here. And if I plot this, and you could try plotting this for this example, and I tried this, and then it looked something like this, right. So, the curve looked something like this. So, basically we know that at p equals 0, there is no chance that I could have generated 1011. So, that is 0, the probability that I see the data is 0. At p equals 1 also it is 0, we already know that. For the remaining, we can calculate these probabilities, and then I can plot this, and what I get here is something of this form, right. And now I can see where does this curve peak. In other words, which is the value of p for which the chance of seeing the data is highest, right. So, the data is most likely for which parameter of p, which choice of p, right. So, and that choice in this particular case, in this example, if you tried, would have been 3/4, right. So, which is exactly the guess that we made, which is by looking at the fraction of ones. But why should this happen? In general, I mean, what is the method here is a question to ask, right. So, and we will see about that in a minute. So what we want to then do is, we have a bunch of potential parameter values which could have generated the data, and then our goal now is to pick one of those values and say, this is what I am going to bet on, this is my guess. And the way we are going to do that is by saying that I will look at the probability that my data is generated given this, the truth is this parameter, and whichever p maximizes that would be my guess, right. So, and this method is quite old, right. So, it has been there since the 50s, and this was proposed by Fisher, and it is called Fisher's principle of maximum likelihood. This might be familiar for some of you. Think of this as a review for estimation if you've seen this before. Otherwise, this is still precursor to what is going to come later. Okay, this is Fisher's principle of maximum likelihood. So, what does that principle say? Well, it says that you write down what is known as a likelihood function L, which is a function of two things. One, the parameter that you are trying to estimate, and it also depends on the data x1, x2 dot 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 xn, right. So, I see the data and I want to think of this as a function of the parameter, because for every value of p, I am going to ask what is the chance that I see this data. Now, how do I write this? I will write this as the probability of seeing x1 comma x2 dot 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 xn. When I write this, it means that that specific value that each of these x1 to xn takes, right. So, in this case, it would be x1 equal to 1, x2 equal to 0, x3 equal to 1, and x4 equal to 1, and so on, right. So, if the true value is p, right. So, if the underlying parameter is p, this is the underlying parameter. Now, how can, so this is a joint distribution, right? So, this is the probability that all these things happen together, that the first toss is x1, second toss is 0, third toss is 1 and the fourth toss is 1, right? So, the probability that all 4 events happen together, but because we have assumed independence, that one event does not affect the probability of the other, I can write this as the probability that x1 parameterized by p times probability of x2 parameterized by p dot 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 probability of xn parameterized by p, right? I can do this, and what lets me do this is independence. This is independence, and now I also know that each of these coins was from the same p, right? So I know that, and so I can write this whole thing as, you know, in a simplified way as product, and this is the sign for product of I equals 1 to n p power xi into 1 minus p power 1 minus xi. This is just a compact way to write this thing. So basically, what does this tell me? If xi is 1, right? So this term is, what does it, when you observe a value of 1, now if the true probability of seeing 1 is p, then I should multiply it with p, right? So which means that this, if xi is 1, this value is p power 1 into 1 minus p power 1 minus 1 0, which is simply p. On the other hand, if xi is 0, this implies this is p power 0 into 1 minus p power 1 minus 0, which is 1 minus p, which is what we want, right? So which means, in, for example, in this particular case, if x1 is 1, x2 is 0, x3 is 1 and x4 is 1, this would be p for this x1 into 1 minus p into this p into this p, which is p cube into 1 minus p. So essentially, the plot that I have done here is that of the curve p cubed into 1 minus p, right? So that's precisely what we have here in general. Okay, so now what is the estimator? So this is the likelihood function, and now we want to define our estimator, which is our guess for p, and that's why I put a hat on top of p to say, to, you know, emphasize that it's a guess, and the guess comes from the maximum likelihood principle, and so this is called as an ML, right? So I'm also writing this as ML, is that argument of p that maximizes my likelihood function, which is in this case just product of I equals 1 to n p to the xi into 1 minus p power 1 minus xi, right? So this is what this is the function that I want to maximize to get my guess for p. Well, this is a function which has a lot of products. Typically, it's easy to deal with sums than products. So what you could do is you can take the logarithm of this function, and in fact, you can look at argmax of p, the logarithm of product of I equals 1 to n p power xi into 1 minus p power 1 minus xi. Now remember, this is fine because logarithm is a monotonically increasing function, which means that if there is a p hat which maximizes the original function, that means that the function's value at p hat is greater than the function's value at any other point. Now if I take the logarithm of it, because it's of its monotonicity, the log of the function's value at p hat will be greater than the log of the function's value at any other point, and so it is okay if I either maximize the original function or the logarithm of it. The point where the maximum occurs does not change, right? So because log is a monotone function, increasing function, I can do this. Now things become simpler. Now this becomes argmax over p, sum over I equals 1 to n, and that's the power of log. Products become sum. This becomes xi log p plus 1 minus xi log 1 minus p. Now this function happens to be a nice concave function. Don't worry if you've not seen that term, that's fine. So this is a function which has a, you can maximize this by taking the derivative and setting it to 0, right? So now this is take this as an exercise. Take derivative of this function, treat this as a function of p, derivative of L of p, in fact log L of p, log L of p, treat the likelihood function, this is the log likelihood function, set it to 0, to get our guess p hat ml as 1 over n sum over I equals 1 to n xi. If you did that, if you had taken the derivative, set it to 0, and I urge you to try that out, you would get that the answer as simply the the average of my data points. This looks like the average, but then it also has a simple interpretation, because my xi is just 0 or 1, heads or tails. Out of the sum, what contributes to the sum is just the ones, not the zeros. So basically the sum counts the number of ones in my data, so this is simply the fraction of ones. Right. So basically here is a method which is called the principle of maximum likelihood, which seems to give us reasonable guesses, right. So my guess for the true p by looking at the data is that value of p which maximizes the chance that I observe this data, and that has led us to guessing the fraction of ones as which was also our intuitive guess. But remember, we have implicitly used two important facts. One is independence of the trials, the other is identically distributed nature of the trials. Yeah, so now this is one example. Now one thing to keep in mind when we are doing this is the following. So let's say we now have data of a different form. We still have x1 to xn, but x1 to xn are no longer zeros or ones. Let's say xi belongs to real numbers for all I. Let's say I collect the height of bunch of 100 people, and then I want to reason about that in a probabilistic sense. Now the height cannot necessarily be 0 or 1, so it can be any value, and so I cannot use the previous model. If I use the previous model, the box with a coin inside that, that's not going to be useful for explaining this data, because that box can explain only data which has zeros and ones. So I need a different box to explain this data, which means I need a different probabilistic model that I need to assume to explain this data. And a natural model in this case would be something like assuming the box, you still have a box with a button, and then our data comes from it. But because our data can be any real value in this case, we want a box that can explain real numbers. And we are going to assume the most simplest thing would be to assume that the box has a Gaussian random variable with some mean mu and some variance sigma, right. So that is, I am assuming xi is Gaussian with mean mu and variance sigma squared for all I. That might be another reasonable assumption to explain this data. Now if I do that, and if I now, let's say we again write the likelihood function like how we had written earlier, which is now for simplicity, let's say we know the variance that generates the data. It's not true in general, right. So if you have a bunch of data points, you won't know anything about the data, but let's make it even simpler and say that we know the variance, right. So the only thing that we don't know is the mean, right. So let's say mean is the parameter that we are trying to estimate. So mean is unknown. Say variance sigma squared is known. So now what is the likelihood function look like? Well, it's a function of mu, sigma squared, the parameters. I mean, one parameter is known, one is unknown, but still it's a function of these two, and of course the data x1 to xn. I see a bunch of data points. Now what is this likelihood? Well, the way we have put down likelihood earlier is that this is the probability that the joint distribution of x1 to xn parameterized by mu and sigma squared, right. So of course I can write this as a product by independence of I equals 1 to n probability of xi by mu and sigma squared. Now what is this probability, right. So let's say x1, the first height that I measured was 162.53 centimeters. Now let's assume some Gaussian distribution with mean 150, let's say, right. So, let's say this is the Gaussian PDF, here is 150, some variance that I know. Now, I am trying to guess the mean, right. So, let's say I start with my guess as 150. Now, and I am asking what is the chance that if I draw a sample according to Gaussian distribution with mean 150, what is the chance that I am going to get 162.53? That is the question that we are asking here, right. So, if we define our likelihood like this, but if you remember, Gaussian is a continuous distribution. So, you can, if you ask for the chance that a random variable that you sample according to a Gaussian distribution falls in an interval a to b, then we know that that chance is just given by the area under this curve of the PDF, right. So, this PDF, if you remember, is e to the minus xi minus mu squared by 2 sigma squared into 1 by square root 2 pi sigma. All that should we know, right. So, now now this is the chance for an interval, but then we are asking what is the probability of a specific value that we have observed, right. So, I stopped a person, asked for his or her height, and then I got the value as 162.53. Now, I want to ask the probability that I see this particular value with some Gaussian with some mean mu. Now, because Gaussian is continuous, this value is going to be 0 for any individual point or a bunch of points, right. So, only intervals will have non-zero values for continuous distributions. And so, no matter what my mu is, this is always going to give me a 0 value, right, because I am asking for the probability of a bunch of points to be generated according to any mu, any Gaussian with any mu, however away it might be from the data or close it might be to the data, it is still going to be 0. In other words, this function, the way that it stands now as a product of probabilities, will give me 0 value for all possible choices of mu, which means this is not able to distinguish one mu from another, right. So, it does not have the capability to distinguish one mu from another. So, it might not be useful in making good guesses, right. So, we cannot really, there is nothing to maximize here because every mu gets a value of 0. So, all mu's are equally good, equally bad, right. So, you cannot really use this function to make a guess. And the problem arises because of the fact that Gaussian is continuous and individual points get 0 probabilities. So, Fisher's proposal was to not use the probabilities and instead replace the probabilities, not do this, and instead define the likelihood of the parameter in this case as not the product of the probabilities, but then instead the product of, or in general, the value that these parameters take, these observations take as given by the PDF of the distribution that generates the data, right. So, you replace probabilities with PDFs. In other words, you want to replace the x probabilities with the joint PDF x1 to xn of x1 dot xn parameterized by mu and sigma square. Now, PDFs behave similarly with respect to probabilities for a lot of cases. In fact, if the data points are independent, PDFs will factorize. So, this can be written as I equals 1 to n f of xi parameterized by mu and sigma square. What does this mean? This means that I am looking at the bell curve's value at xi, right. So, I am not asking for the probability of seeing this point is 0, but then the value that this point takes as given by the PDF is not 0, right. So, that is some non-zero value. It may not even be between 0 and 1, but it is some non-zero value that I can use as a proxy in some sense for the probabilities, right. So, that's the proposal of Fisher. And in fact, what is this going to be? We know what this is, right. So, for the Gaussian, so this is asking if the true mean is mu and the variance is sigma square, what is the density at a particular value xi, and we know that by definition is 1 by square root 2 pi sigma e power minus xi minus mu squared by 2 sigma squared, right. So, the same mu and 2 sigma squared, but then you are multiplying it over different xi's, right. So, that is what this essentially means. So this is our new modified likelihood function. In fact, that's why we call it the likelihood, right? So we don't call it the probability function. If it was always using probabilities, why give it a different name? We are giving it a different name because it's not strictly probabilities, right? So of observing the data. It's the likelihood of observing the data. That's what Fisher called it. And we want to maximize this likelihood function. Now you do the same drill. This is a product of a bunch of things. So you take the log of the likelihood function of mu sigma squared x1 to xn. I'll just do this for completion, only one example. So this is sum over I equals 1 to n, log of 1 by square root 2 pi sigma. Now this is logarithm to the base e, so you can do this as minus xi minus mu squared. The logs and the exponentials cancel, and this looks like this. Of course, we are trying to maximize this with respect to mu, because we want to find that value of mu that maximizes the likelihood. So this term does not have mu, so I can remove this term. It is not going to contribute to my maximizer. In other words, I might as well maximize sum over I equals 1 to n minus xi minus mu squared. I can even remove 2 sigma squared because that's I'm assuming as a constant, right? So that doesn't really affect my maximization. So I want to find that argmax over mu, which is mu hat ml, right? So that's going to be my guess, which is an argmax over mu, the negative of this, which again you can take the derivative, set it to 0, and please do that. Try that out. It's just 2 steps. This again happens to be 1 over n sum over I equals 1 to n xi. What does this tell us? This tells us that if you have a bunch of data points, and this is the important part, that if you assume that this data is generated according to a Gaussian with certain unknown mean mu, then the best guess according to the maximum likelihood principle for this unknown mean mu is the sample mean. Now, it might feel that, well, what's the big deal, right? So we could have anyway taken the sample mean and it would have been a good guess for the unknown parameter. But this is a good guess. The sample mean happens to be a good guess only, or at least not, I should not say only, in this case where we are assuming that the underlying data comes from a Gaussian. If I change that assumption to a different distribution, maybe I have some domain knowledge which makes me believe that the data is not coming from a Gaussian, but then it comes from, let's say, a Laplacian distribution, for example. That's a different probability distribution, which it looks like a Gaussian, but then it's more sharp at the peak. Then if I do a principle of maximum likelihood, it's no longer going to give me the sample mean. It will give me something else, right? So in fact, it will give me the sample median, which means to say that your estimator is very closely tied with the probabilistic model that you assume that generates the data, right? So it's always, the sample mean may not be a good guess. It depends on what model you believe generates this data. If you believe in a different model, the guess is going to be different, and our method adjusts to the model, right? So because the method essentially tries to use the PDF of the model that generates the data, and so it works well for the model that we use. So that's a point that I just wanted to mention, and in general this is a very general purpose method, right? So it doesn't make it's a simple idea, right? So you put down a model, whatever model it might be, you put down that model, write down this PDF of that model, or if it's a discrete distribution, the probability of that model, and write down the likelihood function of the parameters, maximize it, right? So it's as simple as that. It's not just as simple, it's as general as that. That's more important, right? So it's super general in the sense that once you have the model, you have a method to get an estimator, right? So these estimators may not necessarily be very intuitive a priori. In this case, perhaps it is intuitive. In the previous case of the coin toss, it was perhaps intuitive. It's good that it matches our intuition when we do have intuition about what might be a good guess. But even if we don't have intuition about what might be a good guess, the method is robust enough that it can give us some estimators. And that's why this is a very super popular method in general in statistics and machine learning. Okay. Now, so this is one side of the story, right? So this is the summary, so to say, of the principle of maximum likelihood. Now, of course, if you are in a statistics course, you would try to understand, why is this a good estimator? Maybe somebody smart tomorrow might come back and say that, hey, I have another estimator which is a better estimator, and then you have to, argue why maximum likelihood is a better estimator than what they might have, and so on. And that's what a statistics course would do, right? So they will try to argue, good properties of the maximum likelihood estimator, and in cases where it can be in general, it will give you very good estimators, right? So and in some cases you can argue that you cannot get any better than a maximum likelihood estimator, right? So in certain well defined ways, you can argue that it is the best that you can ever get, and so on. But because this is not really a statistical course, we are not going to dwell deeper into the specific properties of the maximum likelihood estimator itself. We will agree that it's a good estimator. It typically is an estimator that gives you reasonable guesses, and what we want to use is somehow ask the question, fine, so this is a good estimator, given data it gives me good estimators, is there something else that might be typically available in practice, and if so, is the maximum likelihood estimator still the best thing to do, or is there something else that one can do? Of course, I am being vague here, so let me make that a little bit more precise, and then we'll try to see how you can potentially come up with different estimators which might be in some cases better than the maximum likelihood estimators.